Hi everybody, and welcome to the 7th lesson in Unit 5, which deals with how to back up the truck and solve some differential equations. On today's show, the shortcut, a process known as tabular integration. Tabular integration. I have seen it work 1,000 times. I am positive there is good math behind it. Here's the basic idea. What I'd like to do is I'd like to find the integral of x cubed e to the x dx. How do you find the integral of x cubed e to the x dx? Well, we would do integration by parts, where we would let this be the u and this be the dv, and we would take the derivative of x cubed, get 3x squared. There'd be some integral with a 3x squared dx in it, and we'd say, well, I don't know how to do that, but it's better than what I had before. And so we'd do another integration by parts, and we'd get some integral with a 6x dx in it, and we'd say, well, I don't know how to do 6x e to the x dx, and we'd say, well, I don't know how to do that, but it's better than what I had before, so I'd do it again. So what tabular integration does is it allows us to take these problems where we know we're going to have to do integration by parts and by parts and by parts again, and come up with a simple answer very quickly by recipe. And the way we do that is we say, well, I know what the u function would have been. It would have been x cubed, and it would have been the polynomial all along. And so we just take derivatives of x cubed until they run out. We just take derivatives of x cubed until they run out. Then we have a dv column, and in the dv column, we have our e to the x. dx is understood in the process. And we just take antiderivatives of e to the x until everybody's got a horizontal partner, like so. Okay? So here's what happens. Everybody pairs up with somebody else. But they don't pair up straight across, they pair up diagonally to the right. Diagonally to the right. Nobody pairs up with e to the x at the beginning. Nobody pairs up with 0 at the end. Now, if you remember, integration by parts is this whole business of uv minus the integral of v du. And that minus gets replicated over and over and over again. So we keep track of these products. We're going to multiply everything on green arrows. We take the product of x cubed and e to the x and maintain the sign. But for the next product, we change the sign. And for the product after that, we change the sign again. And for the product after that, we change the sign. And so the signs alternate plus minus all the way down. If we do that, then our integral is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6e to the x plus a constant. Tabular integration helps us do integration by parts over and over and over again quickly. It is the world's awesomest shortcut. Permit me to demonstrate one more time. Integral of x squared cosine x dx. If we were to do integration by parts, we would let the u be the x squared, and the rest of it would be dv, and we'd take a derivative, we'd take a derivative of the u so that we could do the integration by parts. We'd get an integral with a 2x something in it, and we'd say, well, I don't know how to do that, but it's better than it was before, and so we take derivatives of x squared until they run out. And then we take antiderivatives of cosine x until there are 4 things in the column. antiderivative of cosine x, antiderivative of sine x, antiderivative of negative cosine x. And then we take products. Take this product, keep the sign. Take this product, change the sign. Take this product, keep the sign. If there was another one, we'd take that product, change the sign. Keep change, keep change, keep change, all the way down. So what is our integral? Our integral is x squared sine x minus a negative 2x cosine x plus a negative 2 sine x plus a constant. Integration by parts allows us to, tabular integration allows us to do integration by parts over and over and over again. Oh heck, I'll go one more. What if we're dealing with a definite integral? Oh no, a definite integral? Yes, a definite integral. Oh, I'll go. What about that? What about that? Well, in that case, I know that this is going to be the u part, and this is going to be the dv part. And so I'm going to have a u column where I take derivatives of x squared until they run out. That's always the easier part. Then I'm going to have a dv column where I'm going to take antiderivatives of sine 2x. Now the antiderivative of sine of something is opposite cosine of that something, but remember, anti-differentiation, this is a u substitution problem, and by now you're savvy enough that you know that we're just going to throw a 1/2 in the front. You're savvy enough. You've figured that out. So antiderivative of negative cosine is negative sine, but we're going to divide by another factor of 2, and then antiderivative of negative sine is positive cosine, and you're savvy enough to know we're going to divide by another factor of 2. And so how does this go? Take that product, keep the sign. Take that product, change the sign. Take that product, keep the sign. And so what have I got? I've got a negative 1/2 x squared cosine of 2x minus a negative 2/4 x sine 2x plus a 2/8 cosine 2x, evaluated between 0 and pi over 2. So we sub in pi over 2. Let's see, cosine of pi, that's -1. So that -1 is going to multiply by a -1/2. That's a positive 1/2 times x squared plus sine of pi, that's 0, plus cosine of pi, that's -1/2. I'm sorry, no, it's not. It's -1. So that's a -1/4. Minus what we get when we sub in 0. Well, when we sub in 0, the x squared is 0. Then this x is 0. And then this is cosine of 0. That's 1. So that's a 1/4. But we subtract that out. So what do we got? We got pi squared over 8 minus a 4th minus another 4th. Tabular integration helps us to do integration by parts over and over and over again. It is a beautiful thing. I hope you enjoy the shortcut as much as I enjoyed bringing it to you. Next time, differential equations that can be solved through separation. Awesome. We'll see you tomorrow.